The last section in this chapter is about Le Chatelier's principle. Le Chatelier's principle is a very important qualitative part of this chapter. Le Chatelier's principle states that if you change something within our equilibrium system, so add something or take something away or heat it up or change its pressure or something like that, then the equilibrium is going to shift either to the right or to the left in whatever direction will reduce that change. That's Le Chatelier's principle, and you're going to be using that a lot. The lab that we're going to be doing is going to be about Le Chatelier's principle. So let's see how this works. So let's say that we have some kind of reaction here. We have this reaction right here. All right, and there's a couple of things that we could do. First off, we could add more X to this reaction. Okay, I add more X here. What's going to happen if I add more X is the reaction is going to shift in a direction that reduces that change. So if I put more X in, it's going to go this way to try to use the X up, and it's going to make more Y. So if I add X, it's going to shift right. If I add Y, it's going to shift left. That's the first part of Le Chatelier's principle. Now if I take some stuff away, let's say I remove X, well, my system's going to want to make more X, so it's going to start using up Y to try to make X, so it's going to shift to the left. If I removed some Y, it's going to shift to the right. So if I remove some reactant or product from the system is going to shift towards that removed component to try to replace it. These two ideas are incredibly important in Le Chatelier's principle. You need to be sure that you know those. Pressure is also something that can change where a reaction lies. However, it only affects gases. It does not affect solutions, and of course will never affect pure solids or pure liquids. Ways that you can change the pressure of the system is you can add or remove a gaseous reactant or product. You can add an inert gas. The inert gas is not actually going to react with anything, but since it adds more gas molecules to the chamber, that increases the pressure as well. Of course, you can change the volume of the container, and that's going to change the pressure. Decrease the volume is going to increase the pressure. So let's see how pressure changes affect the system. When you have a container and you change the pressure, like if I reduced the volume of this, then what's going to happen is the reaction is going to shift in whatever direction is going to reduce the total number of gaseous molecules in the system as well. So if I have a container that has a bunch of gas molecules in it, and I take the container and I shrink it, then what's going to happen as a result is the pressure increases. But when the pressure increases, the system is going to naturally shift in whatever direction will decrease that pressure, try to put it back to where it was. And so as a result, it's going to shift in whatever direction will reduce the number of gas molecules. So if we take a look at this example right here, here in this example, we have a reaction where on the left it has a total of 4 gas moles. On the right it has a total of 2. And so if I decrease the volume, it's going to shift over to the right to try to make fewer gas molecules to kind of keep the pressure down where it was. If I increased the volume, it would shift back to the left to try to make more gas molecules to keep that pressure where it was. It always shifts in whatever direction will try to keep the pressure the same. So this is just another extension of Le Chatelier's principle. If you change the system, it's going to shift in whatever direction tries to put the system back in its original equilibrium. Now again, these types of changes with pressure will only affect gaseous systems. It will not affect aqueous systems. Now the next one we're going to look at is how temperature changes affect equilibrium. changes in temperature are going to affect our equilibrium in a very similar way. If I change the temperature, my reaction will shift in whatever direction is going to try to negate that change as much as possible. The key on temperature changes is whether the reaction is exothermic or endothermic. If you have a reaction that is exothermic, then that means it releases energy, gets hot. So that means that energy is acting a lot like a product in a reaction. So for something like this, if you increase the temperature, that means you're adding more of this, it's going to shift the reaction towards your reactants, towards the left. Now if you lowered the temperature, it would go the other way. For an endothermic reaction, you're going to have the opposite happening. Energy is acting like a reactant. It's using energy to make a reaction happen. So if I increase the temperature, if I increase energy, it's going to shift away from that increase. It's going to make more Y, so it's going to shift to the right. If I decrease the temperature, it would do the opposite. If I reduce the amount of energy, then it would shift back towards the left, trying to make more of our energy and make more of our X. Now, one of the unique things that happens in these types of reactions that doesn't happen with others is that whenever you do this, it will actually change the value of K as well. In our other reactions, the K value never changes. The reactions shift, the concentration shift, but K stays the same. But if you change temperature, you change K as well. And K will change directly related to that product over reactant ratio. If you have an endothermic reaction, like this one up here, endothermic reaction, and you increase this, it's going to shift over to your product side, and since it's products over reactant, if your Y value increases, that's going to make your K value go up too. Okay, the exact opposite happens in an exothermic reaction. If you increase temperature here, it shifts over to the left. You're going to have more X, therefore your K value will go down. Now again, the exact opposite is going to happen if you decrease the temperature. And again, the K value changes only will happen with temperature changes. They will not happen with any of the other changes that we've been going through. So let's take a look at some example problems. In this example problem here, they give us an equilibrium reaction, they give us a value for delta H, and they ask us what's going to happen if we do some things to it. So on letter A, if I add some into O2, actually, I'm sorry, that should probably say N2O4. If I add some N2O4, it's going to shift towards that way, right over there, so it's going to go to the right. On letter B, if I remove some NO2, so I remove some of this NO2 right here, again, it's going to shift in whatever direction tries to fix that, so it's going to shift again to the right. On letter C, we're going to add some N2, and that increases our total pressure. When you increase the pressure, the reaction is going to shift in the direction that decreases the pressure. So it's going to shift in the direction that makes less moles of gas. So it's going to shift this way because there's a 1-to-2 ratio here. So it's going to shift over to the left. On letter D, the volume is increased. This does the opposite. When I increase the volume, it's going to shift over to the right because it wants to make more gas particles to try to get that pressure back where it was. And then on letter E, our temperature is decreased. To figure out what's going on there, I want to look and see if it's endothermic or exothermic. This is a positive value of delta H, so it's endothermic. Since it's endothermic, that means that my energy is acting as a reactant. I'm having to put energy into it. So if I decrease my reactant, is going to shift towards the reactants, going to shift towards the left in order to try to minimize that change. And then lastly, catalyst. Catalysts only change how fast it's happening. It does not change K. It does not change the composition of the equilibrium mixture. It does not affect equilibrium whatsoever. It just makes it reach equilibrium faster. That's all that catalysts do. They affect rate. They don't affect K.